In this video, we'll talk about the naming of petrochemicals and pay particular attention to organic halides. So far, we've talked about the naming and properties of hydrocarbons, but there are another group of chemicals out there known as hydrocarbon derivatives. These compounds come from hydrocarbons, which as you recall contains carbon and hydrogen, but then these derivatives also have one other element, usually an oxygen, a nitrogen, or a halogen, and we'll denote all halogens with the symbol X. For ease of naming, we're going to name these compounds according to regular hydrocarbon naming rules. All of these derivatives have what's called functional groups, and these are groups of atoms arranged in a particular pattern that determines the most important chemical and physical properties. We've already talked about the aliphatic compounds, the alkanes, alkenes, and alkynes. And the alkenes, remember, have double bonds, and the alkynes have triple bonds. We also then talk about the aromatic molecules, and these have benzene or phenyl groups. Now we're going to talk about alkyl halides. The halides refers to the halogens, which are the chlorine, fluorine, bromine, and iodine. Another functional group that you should be aware of are the amine group. They have the NH2 atoms attached to carbon. Alcohols have an OH attached to the carbon. In an ether, an oxygen is the linkage between two different, or sometimes the same, carbon branches. And for our last group, these have what's called the carboxyl groups. The carboxyl group is a carbon double bond with oxygen. And these two additional bonds that the carbon can form can be bonded to other things. In an aldehyde group, the carboxyl group is at the end of the molecule, therefore one end of the carbon bond is bonded to an H. In a ketone, the carboxyl group is bonded to two other carbon molecules on the left and the right. In a carboxylic acid group, one end of the carboxyl group is attached to an OH, and this is called carboxylic acid. In an ester, the carboxyl group is attached to an O, another carbon, and to some other carbon on the other side. And lastly, in the amide groups, the carboxyl group is attached to an amine group here. All of these are different in terms of their chemical and physical properties. The first class of derivatives we'll talk about are the organic halides. You should note that these are also referred to as alkyl groups because alkyl refers to the alkanes, and sometimes they're also known as halogenated hydrocarbons. In these compounds, one or more of the hydrogen atoms have been replaced with a halogen. Again, this is fluorine, chlorine, bromine, or iodine. Many of these organic halides are toxic. Two examples are DDT, which stands for dichloro diphenyl trichloroethane. It was used as an insecticide, but it was found to weaken bird egg shells and therefore destroy the eggs. Therefore, it has been banned in most countries. Another toxic organic halide is PCB, or polychlorinated biphenyls. These were used in industrial applications such as electrical transformers, but they are no longer in produce. But the electrical transformers that are out there in the field, when they break down or when they're replaced, produces a source of toxic PCBs. Let's talk about the properties of these organic halides. Many of these compounds can be polar or nonpolar. The hydrocarbon end, remember the end with the carbons and hydrogen, tends to be nonpolar, whereas the halide end tends to be polar. Because of this polar molecule, they have higher boiling points because not only do they have London dispersion forces, they also have dipole-dipole intermolecular forces. Despite their polar end, they are still very insoluble in water, but slightly higher than similar hydrocarbons because their halide end offers them a slightly polar molecule, which offers them a slightly higher solubility in polar compounds such as water. Now, because one end of these molecules is still nonpolar, they're very good solvents for organic materials such as fats and oils. Not only are they good solvents, they are also very good solutes in fats and oils. It is also because of this solubility that they are a significant source of biomagnification. Which you have learned in your biology classes as the accumulation of toxic properties in the higher end of a food chain. In terms of naming organic halides, we use the same rules as though we were naming branched aliphatic compounds. However, the names are now slightly different. For fluorine, we call it fluoro, chlorine becomes chloro, bromine becomes bromo, and iodine becomes iodo. So our example here, CHCl3, because there are 3 chlorines attached to a methane molecule, we call it trichloromethane. Let's try a slightly more difficult example. First of all, we identified the main chain of this compound. Here we see it's a 6-carbon compound, therefore we know it's going to be hexane. Next, we look at the branches. We note that if we are to count from the right to the left, 1, 2, 3, 4, 5, 6, the branches will have lower numbers. And we note there are 2 bromine molecules at positions 2 and 4, and 1 chlorine at position 3. And remember, we are going to arrange it in alphabetical order, so therefore this becomes 2,4-dibromo 3-chlorohexane. If there is a tie in determining which end do we number as number 1 to produce the lower number branches, we will give a higher priority to the higher molecular weight elements. Therefore, bromine has a higher priority to chlorine, which is a higher priority than fluorine. In this naming example, we have to use the priority rules to determine which position is carbon number 1. We note that the main chain, is this cyclohexane. However, there are 3 branches. There are 2 bromines and there's 1 methyl. Because the molecular weight for bromine is higher than the molecular weight for carbon, we are going to give priority to the bromine ones. Therefore, we're going to name this 1, 2, 3, 4. Therefore, our bromines are attached to positions 1 and 3, and there is a methyl group at position 4. Therefore, our final name is 1,3-dibromo 4-methyl cyclohexane. One way halogenated compounds can be formed is through addition reaction. Addition reaction is the addition of a small molecule, such as hydrogen or a halogen, into an unsaturated compound, such as an alkene or an alkyne. These usually happen in the presence of a catalyst, which lowers the activation energy, which really means it speeds the reaction up. Here we have an example of ethylene reacting with chlorine gas to produce 1,2-dichloroethylene. These reactions are favorable because a carbon-carbon bond is more stable than a carbon double bond or a carbon triple bond. In a double bond or a triple bond, all the electrons are crammed into a small space. There's a lot of repulsion going on, and it's unstable. A carbon would much rather have all of its 8 electrons in a tetrahedral shape, so that its electrons are spread out apart. The second type of addition reaction is a hydrogenation. Here, hydrogen is added to a double bond to produce a fully saturated compound, butane. It can also react with triple bonds. It will react with propyne to produce propane. Notice here 2 moles of hydrogen is used because there are 2 bonds to be broken in propyne. If an alkene is the reactant, then it can only react with 1 mole of an additional compound, either a hydrogen or a halogen. However, in an alkyne example, the reaction is limited by the number of moles of the reactant, the hydrogen or the halogen. Here we have the reaction of ethine with bromine to produce 1,2-dibromoethene. So we can see that in the presence of 1 mole of bromine, 1 bromide ion or atom will be added to the left side of the triple bond, and another bromide atom will be added to the right side of the double bond. If there is more than 1 mole of bromine available, then a second reaction with the 1,2-dibromoethene will occur. Here we can see that there is a double bond available for another addition reaction. At the end, you get 1,1,2,2-tetrabromoethane. In this reaction, there is sufficient bromide atoms to fully saturate the ethine compound. Another way that organic halides can be produced is through the use of substitution reaction. As the name suggests, one of the hydrogen is substituted with a halogen. This occurs in a saturated hydrocarbon, either an alkane or aromatic molecule, and it occurs quite slowly at room temperature. Therefore, to increase the rate of the reaction, we can either use light or a catalyst. In general, the formula is that an alkane or an aromatic reacts with a halogen to produce an organic halide. Here, the example is of methane reacting with chlorine gas in the presence of light to produce chloromethane and hydrogen chloride. You'll notice that one of the chlorine molecule has now replaced it on the methane molecule, but the other chlorine molecule is now paired with a hydrogen that came off of the methane molecule. If there are multiple hydrogens that are available for substitution, you will get a mixture of products. Here we have the reaction of propane C3H8 with bromine in the presence of light. There are 8 hydrogen molecules that are available to react with bromine. These 8 hydrogen atoms are located at 2 different carbon positions. There are 2 carbons at the end of the molecule and 1 in the middle. Therefore, when bromine replaces the hydrogen that is in the middle, you will get 2 bromopropane. However, if a bromine reacts with the hydrogen at the either end of the molecule, you will produce 1 bromopropane. These 2 products are formed in unequal proportions, and it's not possible to perform simple stoichiometry at this level. Aromatic compounds can also undergo substitution reaction. However, because the hydrogen on the aromatic compounds are very stable, the reaction rates are very slow. Therefore, the use of light and a catalyst, here in this case of being iron 3 chloride, is required for the substitution reaction to occur. Because there are 6 hydrogen atoms available on the benzene ring, you could have this reaction go 6 times to produce 1, 2, 3, 4, 5 hexachlorobenzene.